In this video, we're going to discuss how to calculate out the Gibbs energy for various reactions. Let's take a look at carbon monoxide plus H2 gas going to formaldehyde. In this case, we're going to look at the delta H of formation. We're going to look at the standard state entropy. For carbon monoxide, it's minus 110, and these are kilojoules per mole. For H2, that is elemental source of dihydrogen. It is 0 for its delta H of formation. And for formaldehyde, it's minus 116 kilojoules per mole. For our entropy standard state values, it is 197.5, and these are joules per mole Kelvin. For CO, 130.6 for dihydrogen, and 219 for formaldehyde. Well, our delta G, remember, is equal to the delta H of our reaction minus T delta S. Now we would need to know these values at whatever temperature we are working at. Your enthalpy and your entropy are usually temperature dependent. Now, within a certain range of a value you know, the temperature dependence is small. And so often we use standard states. We've seen these before for our entropy calculations. In the back of the book, all of our standard states indicated by the naught symbol are at 298 Kelvin, so 25 degrees Celsius. So we can calculate out delta G at 25 degrees Celsius using the values in Appendix B. Or you can find these online. If you can find a data set for other temperatures, you can calculate this out at other temperatures. As long as you're close to 298, a calculation like this will be very close. However, if you get too far away, these become more and more inaccurate the further you get from the value for the temp at which the data came from. So we can calculate out the Gibbs energy at the standard state. This is going to be equal to the standard state enthalpy of reaction minus temperature delta S for this reaction. Delta G naught equals delta H naught of reaction minus T delta S naught. Plug in the values we have. Well, how do we find delta H of reaction? Remember that the delta H of your reaction is going to equal the sum of the delta H naught formations of your products minus the sum of the delta H naught of formation of your reactants. Well, for us here, we know those values. My product is minus 116 kilojoules per mole, minus from that negative 110 kilojoules per mole. So my delta H of reaction is negative 6 kilojoules per mole. Well, if I want to find my delta S, same thing. The sum of the entropies of the products minus the sum of the entropies of the reactants will give me my delta S. My products are just formaldehyde, so 219. Subtract from that my reactants, which was CO at 197.5, plus the H2 at 130.6. When we calculate that out, I'm going to end up subtracting a bigger number than my starting number and end up with minus 109.1. And this would be joules per mole Kelvin. It's negative. Think back to our reaction, we go from 2 moles of gas particles on the left to 1 mole of gas particles on the right. So combining carbon monoxide and H2 reasonably should be less entropic. We have far less gas molecules. There's far fewer rotations, vibrations, and translations one molecule can do than 2 could. Since my delta H and my delta S are both negative, this means my delta G will be negative at lower temps. So this is a reaction that's more favored at lower temperatures. At higher temperatures, formaldehyde can break apart to the carbon monoxide and dihydrogen. Let's see that in our calculation. My delta G naught for this reaction is going to be equal to my delta H. Let's convert it to joules. So negative 6,000 joules per mole. Minus from that my delta S, which is negative 109.1 joules per mole Kelvin times the temp. 298 Kelvin. Well, this becomes negative 6,000 joules per mole minus negative 32,511.8 joules per mole. The kelvins have canceled. Negative minus negative is going to become a positive. So my delta G naught of reaction turns into 26,511.8 joules per mole, or 26.5 kilojoules per mole. It's positive. We're too hot. This reaction doesn't want to occur at this temperature. But we have calculated out what the delta G would be. Because it is positive, this will not be a spontaneous reaction. Our CO gas plus H2 gas going to formaldehyde will not readily occur at 298. But we can identify what temp it would occur at. Remember, the temp of your spontaneity change is equal to the delta H divided by the delta S. So in addition to solving our delta G here, let's find out what temperature we would need to be below to make this be spontaneous. Negative 6,000 joules per mole divided by negative 109.1 joules per mole, Kelvin. Joules per mole cancel out. Our Kelvin on bottom will turn into Kelvin. And what we find is the temp is about 55 Kelvin. At that point, you're not really gaseous anymore. You'd have to set up the system very particularly to make this happen. But you can identify at what temperature that transition between spontaneity and non-spontaneity occurs. Let's take another look here. Well, this is wonderfully handy because we have a table that has delta H formations and delta S values. Delta G is also a state function. And you can imagine reactions where you had some carbon solid plus half a mole of O2 gas forming CO gas. And you could calculate out your delta G for this, which means you could solve a delta G of formation. The same way we can solve delta H of formations from the formation reaction. In our book, in our tables, we will also find that there's a delta G naught of formation value. If you have it, there's no need to go through entropy and enthalpy. It's already been done to solve those formation values. Now, if you don't have those, then entropy and enthalpy are very useful. But we can actually do this reaction more directly by just knowing the standard state Gibbs energies for the different molecules. The Gibbs free energy for the formation of carbon monoxide is minus 137.2, and these will be in kilojoules per mole. H2 is the elemental source, so if you start H2 and you end H2, there was no change. So much like enthalpies, standard Gibbs energies for elemental materials, their elemental state on Earth is 0. And for formaldehyde, we find that it is 110 negative. If we plug these in to find, well, the delta G naught of any reaction, much like the other two, is going to be the sum of the delta G naught of formations of the products minus the sum of the delta G naught of formation of the reactants. Our products, formaldehyde, minus 110, minus from that, negative 137.2 plus 0. So negative 110 minus negative 137. Well, if you minus a negative, you add it. So this will come out 27.2 kilojoules per mole. Compared to our previous value, 26.5 kilojoules per mole, you'll notice a slight discrepancy. This tends to come from rounded values earlier on. A lot of the data tables have been rounded significantly in their construction, and so all these were a little bit off from each other. Well, that's a pretty small difference. It's both the same positive values. They're very close to each other. 700 joules per mole is all it's off by. So depending which route you take, they can vary a little bit. But whether you use the entropy and the enthalpy to solve your free energy, or whether you use the Gibbs standard state formation values to solve that energy, both are perfectly acceptable routes to find the amount of free energy for a given reaction.